Hi, and welcome to Double E's Talk Tech. My name is Daniel Bogdanoff, and my co-host,
Mike Hoffman.
And back with us again is Mike Byers. Mike, thanks for coming on again. Mike is an ASIC planner here on the ASIC design team at Keysight Technologies, so he has a lot of great knowledge and a lot of experience with ASICs here in-house and just kind of the infrastructure and ecosystem of ASICs in general. I thought for this episode we'd talk maybe a little bit more about ADCs. So can you start off, tell us a little bit about an analog ASIC versus a digital ASIC and kind of what that looks like?
Sure. So we kind of break ASICs down. We're talking about ASICs here in Keysight into three camps. One, signal conditioning ASICs, something that takes a signal and tries to make it bigger, higher frequency, lower frequency, et cetera. It's trying to do something to it in the analog realm. And I'll skip 2 and go right to 3, which is a signal processing ASIC, right? That takes in digital information, processes it, maybe filters it, maybe displays it, and maybe sends it off to a PCI Express link to a computer. In the middle is that key part is a converter. Right? It's either an analog to digital converter or a digital to analog converter. And it has, again, depending on which A to D converter, can look an awful lot, have an awful lot of digital content or an awful lot of analog content, where the main difference between, an analog circuit and a digital circuit is, are you working with circuits that flip naturally to a 1 or a 0, or are you dealing with a continuity of voltages between a high and a low voltage rail?
Sure. Now, let's break that maybe down a little more. So an analog ASIC, you say, is signal conditioning, and my understanding is that can be very simple or very, very complex. So like I know, the guys who's just sits right over here, he does a lot of filter designs where it's just like I think he calls it it's called a stripline filter.
Right. And
that's more just hey, we can build it ourselves for, these are arbitrary numbers, for $100, or we can buy it from someone for $200. And, you're kind of a younger engineer, so it's cheaper for us to have you, we to build the stripline filter ourselves. And I think we maybe even fab it downstairs or in Santa Rosa. And it's, less about performance, more about cost there. But then you have analog ASICs that are much more complex, maybe on the front end of an oscilloscope that, maybe not front end of oscilloscope, right. But
well, and it's an interesting point. Even the front end of oscilloscope can have a tendency to be what we call mixed signal, have
sure.
both digital and analog components in it. Now, in this case, we make a distinction between a converter, which has a very high-speed analog path and a very high-speed digital path, right? And a chip that has analog functionality like gain or say trigger level,
sure.
or bandwidth limit on an ASIC, and the control for it. So a digital interface, be it a SPI or an I2C interface to come on to control that chip, and then DACs, again, small little digital to analog converters that are basically running at DC to control what is my trigger level, what is my offset of my oscilloscope, and all that can be integrated into one ASIC. So even many of our analog ASICs have a fair amount of digital componentry in them.
So it's like a digital in and a digital out, but all of the processing is analog based.
Yes, digital in to control, but analog in, analog out.
Oh, okay. Huh. Yeah, that makes sense. And then on the digital side, it's basically just streamlined processing. Is that a gross oversimplification, or?
Well, it's how do you get from, the analog circuitry to the digital representation that you want to send to somebody else for processing of some sort. In other words, how do I get, most simply, say an 8-bit A to D converter would have 256 levels. So how do I, at the lowest voltage, how do I put out a 0, and at the highest level put out a 255?
Sure.
A 12-bit A to D converter would have 4,096 levels, right? So that's, it's more resolution. And so how do you get from what's happening in the analog world to what's, to coming out that digital interface? And how do you do it at a high enough rate to be usable in the modern world?
I remember doing this in my sophomore level double E classes I'll just draw out the circuit diagram for an analog to digital converter. I'm assuming ours are probably a bit more complicated. That big ladder of op amps, if I recall correctly, or
yeah, that's the simplest, right? Is the ladder converter, right? And so or thermometer code, right? You go, it's a resistive divider with a bunch of comparators, and so it turns a voltage from, let's say, 0 to 1 volt. It turns it into either one and a bunch of zeros, or 2 ones and a bunch of zeros, or 3 ones and a bunch of zeros. So that 256 codes comes out as thermometer code, as we say, or 256
thermometer,
bits.
like you can
see it go up, right? The ones go up. So, but you don't want to ship all 256 lines off.
Well, you don't.
So you just so we have to take that thermometer code and turn it into a digital value.
Now,
that's the very simplest processing that happens in an A to D converter. So there's a little, even in any A to D converter, there's a handful of digital gates to take the output of the analog circuit and turn it into a digital number to be shipped off to somebody else.
So is that roughly the same technique as like SERDES without the Ds?
Well,
so serializer, deserializer.
Yeah. Now, how do you, once you've got this data, how do you send it off to somebody else? And now you have to pick the I/O you want. If it's a very slow A to D converter, you might use single-ended CMOS. To go faster, you might use a parallel LVDS implementation. As you get into the kind of data converters we're working with these days, it's almost always transmitted over on SERDES.
Okay.
So that 10-bit value in the case of the S-series oscilloscope is put on a SERDES and shipped off to the processing element over a SERDES lane.
Okay. A term that I've heard thrown around here is the world's fastest ADC. And that's, I've heard you use it in the hall. I've heard a couple of the ADC, design engineers using it. Can you just expound on that concept a little more?
And please tell me that Guinness World Records came out here to verify that. Get a plaque or...
Yeah.
We sold them an oscilloscope first so they could check it.
Yeah.
So again, why do we design? We do design in Keysight the world's fastest A to D converters for oscilloscopes. And again, we talked earlier in our ASIC segment about we don't make normally what we can buy. And so we're making these because we need faster A to D converters than almost any other application out there. So it comes down to, if you want to represent a 10 gigahertz signal, you need at least 20 gigasamples, right? That's the Nyquist rate. You need at least twice the bandwidth. So you need at least 20 gigasamples. Probably you'd like to use a little more than that, maybe 25.
Yeah.
So, a 25 gigasample A to D converter, that's, you got to produce a sample every 1 over 25 gigahertz, which I think is 40 nanoseconds. Did I do that?
1 over a gig is a nanosecond, so it would be 40 picoseconds?
Oh, yeah, 40 picoseconds. 400
picoseconds?
I think of 40.
Yeah.
25 gig, right?
25 times 40
pico.
Is 1,000. Yeah. Yeah, okay. So you can do math in his head. So
that was a close one. Yeah.
So you have to generate.
That's why he's here.
You have to generate a signal, right, every 40 picoseconds. How do you do that?
Okay.
Right.
And just for those of you watching, we do have an app note and maybe a blog post about how sample rate and bandwidth play together in the real world. So ideal Nyquist scenario, you sample at double the frequency and everything works out. But in the real world, you need a little more than that. So I think we have some cool stuff. You can just Google, Keysight sample rate app note or something like that. We'll put a link in the YouTube description also.
If you're under the age of 70 and can't find that app note on Google, then I don't know what to tell you.
Then it's not there. Yeah.
So the other half we talked about, there's the speed of the A to D converter, but what's often missing is and then there's the vertical, right? Or the resolution. We talked about number of bits, and we talked about speed, and those are the things that allow you to measure something. And often in the high-speed world of people designing SERDES or optical communication systems, it's timing measurements. It's the ability to measure time accurately that's most important. They're measuring jitter, et cetera.
Okay.
But what's missed often is that it's both those things that allow you to accurately make a time measurement. You have the best, highest sample rate in the world, but unless you have low noise as well, you can't tell where that edge placement is. And having low noise gets harder and harder as you have more and more bandwidth.
Because noise is proportional to your bandwidth.
Yeah. And so And so it's getting the right combination of those two things that's important in ADC design. And normally, we have a tendency to oversimplify the specifications of an A to D converter into sample rate and bits. Right? Those are the two easiest ways to think about how accurately are we measuring the time and how accurately measuring the voltage.
Banner specs, right? Yeah.
But you peel back the onion a little bit, and there's all kinds of other secondary things you need to worry about. Number one being bandwidth, right, and frequency flatness, but also in the horizontal dimension, but also your noise. Right, so it's actually much easier to add bits to an ADD design than it is to decrease the noise. So
stay tuned for our new 50-bit ADC.
Yeah, right.
I'm doing an oscilloscope near you.
And so
There's so much data.
Beyond that, there's beyond the noise floor, which dominates in oscilloscopes because they're so wide bandwidth, is the SNR. I'm sorry, the SFDR. How far down are all your distortion products?
Spurious free dynamic range.
Yeah. And so it's that combination of SFDR and SNR and bandwidth and flatness that really measure just how good an A to D converter is. Beyond that, there's some even third tier type of things you need to worry about, in particular for instrumentation. A lot of any error codes are a bad deal. There are some architectures in A to D converters that are prone to error codes.
So explain what an error code is, what makes it pop up.
Sure. In the case of that thermometer we were talking about, right? If one of those, if you are off by 1 bit, well, okay, you got value 37 out instead of 36. That's no big deal. But as you get into some folding architectures and some successive approximation type architectures, you can get bits more significant bits that are off. So instead of getting 36 or 37, you accidentally get 37 plus 128.
Right.
Every once in a while.
So if the 4th bit is off instead of the 8th bit off,
right?
Then
And so so those are. They may not matter that much in a communication system, where if they happen once in a billion, once in a trillion times, the chance of them forcing an error that the communication system can't recover from is small. But if you put that in an oscilloscope,
you're drawing
and you're drawing a second across screen, and all of a sudden there's a big spike in the middle of it, you can send a customer off for days trying to figure out what this spike that only happens once in a blue moon when it's actually his instrument.
With seemingly no correlation to their system.
And so there's some additional things besides the basic horizontal and vertical resolution that we need to watch out for on the instrumentation side.
So when you talk about noise, is that something internal to the ADC, or is it how you kind of kit it out and give it signals?
Yeah, in a well-designed system, it's a combination of both. Right? If your ADC is contributing most of the noise, you've picked the wrong ADC. But if it's contributing no noise to your system, you got some really garbage amplifiers out in front, and you need to work on them. So we start in an instrument with a noise budget on how much noise is contributed by the various pieces of the chain. And then we go off and say, okay, you front end designer, you get so much noise. A to D converter designer, you get so much noise. Somebody else gets so much noise. And of course, that all gets renegotiated as time goes on. But you got to start from an overall system viewpoint of how do you divvy up the noise between the pieces of the design.
Okay. Now, like an ADC seems kind of like the ultimate ASIC challenge to me because it's so much a crossover of the two.
And it's not only there's some hard analog designs, strictly straight analog design, because of the speeds you're trying to accomplish and the fact that there's digital, you're pushing into some of these what we call fine geometry CMOS process to do our A to D converters in these worlds because they're a mixture of analog and digital. So it's that, it's working in processes that people haven't worked in before, processes that are really geared more towards doing digital design than analog design. That I think is part of it that makes it difficult.
Okay.
Now, they have the advantage from the analog side of somebody else is handling all the high power requirements, and what happens that we never ask the A to D converter to take 100 volts in like we do the front end of an oscilloscope, et cetera. So there's, I don't want to say it's, somebody's going to come get mad at me if I tell them that the A to D converters are hard and everything else. Some of the guys say, yeah, right, that's right.
That was not my intention, yeah. Like, yes, my job is the hardest in the world. I'm having question blanks today.
Okay. Well, roll the clock back. Maybe this isn't a question that I didn't hear the answer to it. We talked about Keysight here as the fastest ADC, right? We're talking about 25 gigasamples. Is that? I know we have faster.
No, yeah. Let's see. What's the fastest thing we have shipping? Is 80 gigasamples per second?
80 to 100 shipping now. I think we're up there. I don't know.
Yeah, I think it's 80.
Okay, 63 gig real time. I think it's 150.
No, 160. That's right. Sorry.
So 160 gigasamples. Okay, we were going to have you look up a scope for us, see where our ADC was, but
it's one. Good. Sorry, yeah, and you can interleave. You're right. 80 gigasamples for the 30 gigahertz channel, and interleave two of those gets you to 63 gigasamples, supported by 160 gigasample sample rate. Now that's not one physical A to D sample, right? That's a system that accomplishes that.
And that's
the samplers out in front,
okay,
right? That distribute the samples analog to the A to D converters that then translate those. And that whole architecting of the sampling system is again one of the big challenges.
Without revealing trade secrets, can you talk a little bit about interleaving and how that works? How do you coordinate that?
Sure. There's a couple of, if you think about it very simply, you have an A to D converter. If you want to double your sample rate, you put two A to D converters.
Right.
And feed the one system, one thing to both. But you have two problems. One, you're taking the samples at the same time. Right, and two, you're not increasing your bandwidth. So if your A to D converter has enough bandwidth to sample the system you want, then you can just offset the clock in one versus the other, and then take the sample odd, even, and you end up with double the sample rate. But you haven't increased the bandwidth, right? Of the A to D converter. So if your goal was not only to go from 80 gigasamples to 160 gigasamples, but also to go from 33 gigahertz to 63 gigahertz, you haven't accomplished your goal, right? You've only gone from 80 gigasamples to 100 gigasamples. So then again, you need a sampler out front that will take samples and feed them, take the samples at the very high sample rate and feed them at a lower bandwidth to the even and the odd, or in many cases even
like a switch, basically, like a high speed train conductor switch.
At the simplest level, it's a switch, but then we have to talk about the inter-symbol interference, how to keep the sample that you're going to take in A to D converter A different than in A to D converter B. If you had an infinitely fast switch, that would do that, but you don't have an infinitely fast switch. So what frequency do you response do you want in basically the IF of your sampler? Is a long discussion, and there's a long history of different approaches, and something we continue to evolve here at Keysight.
Cool. Yeah.
Only 7 trade secrets revealed. You're not fired this time. You're good.
Let's see. So it sounds great, right? I can take my inexpensive A to D converter. I can interleave a bunch of them. I don't get more bandwidth, but if I put a sampler out in front, I can get more bandwidth too. What are the drawbacks? Well, getting everything to match up is hard. Sure. And so you need a lot of adjustability, not only in the A to D converters, but in the samplers to try to get everything calibrated and aligned, because anything that you don't get lined up, let's say just, the Q levels of one A to D converter are higher than the other.
Oh, sure.
And so you got one that's high and then 3 that are low.
Got a whole bit of noise, basically.
Yeah. Well, and you're not only that, but you're going to see a repeating pattern. Yeah, you're going to see a repeating pattern of high, then low, then low, then low, and high. And
so you get frequency spurs, basically.
Yeah, and so you'll get a fixed frequency spur even with no signal in, right? Just the offset. But beyond that, once you start putting signals in, you start to get what we call gain spurs as well, where where you put one frequency in and you get multiple frequencies all over across screen.
Sure.
So I mean it's true of all interleaved AD converters, but we try to minimize that as much as possible, and that can be done again with analog calibrations, with DACs, with adjusting things. There's also some DSP we can do to remove some of that after the fact.
Okay. And I know that like you can actually plot out the noise floor based on x-axis of sample rate, and as you hit you start to interleave, you just see the entire noise floor go up a little bit just naturally.
So part of that is if you're increasing the bandwidth of the system when you do that.
Sure.
The other half of this is if you don't have this offset calibration.
Okay.
Because it'll, if you take every other sample and move it up and down a little bit, it'll look like noise. But mostly we should hopefully calibrate almost all of that out. And so what you're seeing is more bandwidth is more noise.
Okay.
Right. Twice the bandwidth is going to give you 40% more noise.
Okay. And I know we've seen another test and measurement equipment vendor doing triple interleaving instead of double interleaving. And we see that pretty clearly in the noise floor.
Yeah. So, again, there's many ways to interleave AD converters. The devil's in the details, and it's really what kind of SNR and SFDR can you accomplish?
Sure.
In the end, not only do we have multiple samplers that sit out in front of AD converters, internally our AD converters are made up of many smaller AD converters that are running at slow slices. So keeping everything interleaved, there's no real limit. There's no one way of interleaving.
Sure, that makes sense.
Works better than the other.
Okay. Now, in-house, we have a analog ASIC team, a digital ASIC team. Who does the ADCs? Is it third team?
Third team.
Okay. So we have an ADC team, and that's...
we have a team that works on ADCs and DACs.
Yeah. We actually, one of them, Mike, did a talk recently for the Society of Women Engineers group on site, and we got it filmed, so that'll be on our YouTube channel. I'm working on chopping that up.
Mike did the talk on the front end.
Yeah, it was really good. So you can look for that on our YouTube channel.
Mike who?
Well, Luhan.
Okay.
So also a golfer, I think, right? Yeah. I know you guys are you have golfed before. I'm not a big golfer.
No, it's Mike McTighe.
Oh, I'm sorry.
Yeah,
no.
different Mike.
Mike is, okay.
I was wrong on that one too.
Well, that was awkward. And that was captured just for you on the podcast. So congratulations. Any other ADC questions or any other ADC points you want to hit before we call it a day? I know we're at wrap up time.
I think it's just one of those ADC technology, just like many other things, just in the electronics world, is just marching forward at an incredible rate. And what's available out there in the commercial off-the-shelf world is what's enabling 5G, 100, 400 gigabit, terabit Ethernet. More and more and more things are moving out of and being processed by analog circuitry to have an A to D converter followed by digital signal processing. It's just a fundamental thread that's been as big a part of the change in technology, both ADCs and DACs, digital to analog converters, over the last many years since the advent of the microcontroller in the 70s.
Is processing driven by ADC technology, or is ADC driven by advances in processing technology?
Both, right? There are architectural advancements in ADD technology, but then there are some ADD technologies that, hey, if you have it in a 40 nanometer process, you move it to a 32 nanometer process, the ADD is going to work better and faster. There's others.
Interesting.
That's not as true.
Okay.
So, but they definitely, some of the A to D converters you see published lately, some of the highest speed ones for some of the optical communications groups are in some of the finest geometry, smallest geometry CMOS processes.
Okay.
So they definitely are moving together.
Cool. I think we're out of time. Again, predictions. I'm going to put you on the spot again.
I have an idea that I just came up with.
Okay.
I'm going to float it.
Does it have to do with space or like lasers?
No space lasers.
Where we were last time. Okay.
No space lasers. No, I'm thinking like maybe I should have done this offline, but I'm going to put you on the spot here.
Sure.
What about as well as predictions, a new section like stupid question where I get to ask the guest a really stupid question.
I like
and they
that.
have to answer it.
They have to,
as if it's a real question.
Okay, I approve.
I'll try.
Okay.
All in favor? All right. The ayes have it. Our guest is like, Now, is it going to be the same stupid question every time, or is it like unique?
No.
Oh, okay.
It'll be topic specific.
Okay, I'm going to let you roll on that one.
See how it works out. Okay.
Go for it.
What is your favorite sample rate and why?
This is like the pick a date
Four
game show.
400 megasamples.
I thought you were going to say four.
400 megasamples was one of the first scopes I worked on. Actually, the first MSO, if I get my history right, one of the first MSOs anyway. And we really were worried about whether we needed 400 or 500 megasamples. And we continued to argue it at the lunch table, in the halls, and the whatever. And at one point, our boss just stepped in and said, 4 equals 5. We're going to stop arguing about this. And so I still remember that's one of the fundamental rules of engineering we had for that project was 4 equals 5. So 400 megasamples is my favorite sample.
Classic HP engineering there. Yeah. Awesome. That's a good question.
Thank you. I don't have the prediction though.
No, that'll do. We'll count it. So that's all we have time for. Again, Mike Byers, thank you so much for taking some time out of your busy day planning ASICs to come, impart your wisdom to us and our audience. It's been great.
Thanks.
If you want to learn more about how ASICs are developed, just the high-level process, there's a blog post on that. We'll put a link for that in the YouTube description. You can also subscribe to us on your favorite podcast engine and visit us at eestalktech.com. And that's all for today. We'll see you next time.
Quick request, though, for all of you listening on iTunes, give us a rating. It actually helps us out quite a bit. We want to help broaden our audience a little bit and have some other folks who may be interested in listening. And one great way to do that is through ratings. So let us know what you think.
Yes, definitely thumbs up, subscribe to the YouTube channel, all that. So we will see you next time. Thanks for watching or listening or whatever you may be doing. I don't know if there's another option there.
Thinking about us. Don't do that.
We should end. All right. It's over.
All right. Bye.
Cut.